In the study of dynamical systems, the mixed-slope Collatz symbolic family for the itinerary 101 presents a precise challenge. Our objective is to find the exact analytical value for its topological entropy, denoted as H. Over hundreds of iterations, empirical cylinder counting sequences and truncated two-tower matrix models show a growth rate converging near 1.1255. But numerical convergence to a deep computational bound does not constitute a mathematical proof. This particular system operates via a discontinuous map, which means empirical finite models will eventually fail to capture the true asymptotic behavior at the boundary. Standard continuous constant slope entropy theorems fail here as well. The map is non-surjective and sharply discontinuous at the exact threshold of 2/3. To establish the exact entropy, we must abandon finite truncation matrices entirely. Instead, we have to construct a rigorous algebraic root equation derived from the exact properties of the system. This diagram shows the one-dimensional state space on the interval 0 to 1, separated by a boundary at 2/3. We map this space using two affine formulas, RL of y for the lower branch and RU of y for the upper. Both share an expanding absolute slope of 9/8. Because this uniform slope is strictly greater than 1, all trajectories undergo geometric expansion. Left unchecked, they would infinitely diverge. To control this expansion, we define a forward invariant core. We denote this set as X, representing the precise subinterval from 0 to 3/4. We prove this invariance by evaluating how the map acts on the set. Applying the map R on the core X outputs exactly back onto X. Trajectories jump rapidly across the 2/3 line, but are mathematically forbidden from escaping past 3/4. Bounding this chaotic, infinitely expanding behavior within a strictly forward invariant core provides the geometric prerequisite necessary to map a solvable first return partition. We can now track how state mass fractures, expands, and deterministically returns to its origin by building a structure called a renewal ladder. The 2/3 threshold splits the core into two sets, a blue segment from 0 to 2/3 and an orange segment to 3/4. The blue immediate return set is multiplied by 9/8, stretching perfectly to cover the full core boundary. Because a single application of RL maps this set directly and perfectly onto the total core X, its orbital tracking is instantly resolved. The orange spawn set from 2/3 to 3/4 begins a new dynamic chain. The RU operator takes this space and maps it to a highly compressed seed domain at the bottom of the state space, confined between 0 and 3/32. Since the immediate return set resolves in one step, mapping the total entropy of the system is now reduced exclusively to tracking the eventual return of these spawned chains. This newly spawned seed is subjected to repeated sequential applications of the L branch. Mathematically, every L step multiplies the state space block by 9/8, forcing its length to strictly and monotonically increase. By the Archimedean property, this continually expanding block must physically cross the 2/3 boundary in a strictly finite number of steps. The risk is an expanding step jumping over the landing zone, escaping permanently. However, we rely on an algebraic crossing bound. A prior step under 2/3 multiplied by 9/8 guarantees the subsequent step is mathematically locked strictly below 3/4. Consequently, the crossing chain splits flawlessly. It deposits exact return mass back into the lower boundary and spawns the next sequential seed exactly inside the upper boundary. The Archimedean crossing bound guarantees that no fraction of state mass can ever jump past the invariant core or permanently avoid returning to the threshold. To count these paths accurately, we have to verify if these first return cylinders are mathematically distinct or if they suffer from overlap at their shared boundaries. Recall the strict mathematical definitions of the intervals defined at step 0, the lower return 2/3, and the upper spawn set is 2/3 to 1. We use a half-open boundary convention. Because the exact rational value of 2/3 belongs unambiguously to the upper set, the two intervals share 0 intersection points. Consider two independent paths sharing an identical prefix until the exact threshold crossing. At divergence, one satisfies the condition to take the L branch, cleanly dropping into the return bin. The other takes the U branch, proceeding into the spawn bin. This half-open separation guarantees the first return cylinders are fully disjoint topological sets. To shift from disjointness to completeness, we track the pre-images, the inverse maps of these first return chains. We define an inverse contraction ratio of Q equals 8/9, which governs the shrinking geometry of these pre-images. As the stage M approaches infinity, the total unreturned residual space is bounded by Q to the power of the chain length, and it shrinks exactly to 0. Disjointness absolutely prevents overlap, and completeness guarantees 0 unmapped space. The infinite tiling of the geometric core is flawless. We return to the full invariant core interval X. The synthesis of the prior proofs is visible here. An infinite series of disjoint first return chains perfectly tile the core interval without gaps. This tiling maps continuous space into a discrete framework via the Kraft identity. At stage M, exact length conservation is the ratio of residual space to the total core equals 1 minus Q plus the sum of Q to the power of the chain lengths. Taking the limit as M goes to infinity zeroes out the residual space, balancing the total normalized length of the core perfectly to 1. Executing this translation from continuous geometric dynamics into a strictly discrete equation provides the exact algebraic tool required to extract the system's growth rate. We reformat the balanced length conservation equation directly into its characteristic root format, 1 minus z minus the sum of z to the power of the chain lengths equals 0. We define the evaluation function f of z as z plus the infinite sum, evaluated over the strict interval between 0 and 1. Because every single term in the series sequence is positive, the curve sweeps strictly upward, making it monotonically increasing. A strictly increasing function crossing the value of 1 guarantees exactly one unique dominant positive root. Substituting the known inverse contraction ratio of 8/9 perfectly balances the equation to 1, proving z equals 8/9 is that exact dominant root. The physical consequence for the dynamical system is absolute. The root multiplicity sequence, and therefore the total number of accessible states, must grow at an exact exponential rate of 9/8 to the power of n. The exact topological entropy is established as the logarithm of this exact root, h equals log of 9/8. The Collatz mixed system entropy problem is fully and unconditionally resolved.